So I'll give a quick intro first. So most of the 10 weeks we have been working with CNNs, and we recently transitioned to Mini Rocket, which has shown promising results, though we are yet to have performance metrics on a per patient basis. With Mini Rocket, we've increased our sample size by splitting patient data into chunks, and we have improved our specificity and sensitivity scores, though this is on the chunks instead of per patient. We had hoped to compute these metrics on a per patient basis in time for the demo, though we've had difficulty matching up patient chunks, and therefore we need a little more time for that. Right now, the best scores on a per patient basis are 71, 71 sensitivity and specificity using the CNN. But today we'll be demoing our mini rocket model that achieved 84, 84 on the chunked data.
Well, awesome. We just got Joel. So if all right, I'm gonna ask you to back up to the start, just as we let him get in here.
For sure.
All right. Sorry about that.
Good.
All right. Great. Cool. Well, I think we're just, yeah. So we were slotted to start a little bit late, but I think we've got everybody here. We just got Joel in here as well. So yeah, Brian, if you can kick us off, we'll get started, go through the demo, and then we can give some kind of high level feedback. Then I'll open up a breakout room for you guys to discuss, next steps, turning it over to the team and all that jazz. But if you guys are ready, over to you.
All right, from the top. So most of the program we've been working with CNNs. We've recently transitioned to Mini Rocket, which has shown promising results, though we are yet to have performance metrics on a per patient basis. With Mini Rocket, we've increased our sample size by splitting patient data into chunks, and we have improved our specificity and sensitivity scores there. We had hoped to compute these metrics on a per patient basis in time for the demo, though we have had difficulty matching up patient chunks and therefore need a little more time for that. Right now, the best scores on a per patient basis are 71, 71 sensitivity and specificity, and that's with the CNN. But today we'll be demoing our mini rocket model that achieved 84, 84 on the chunked data. So a quick recap of our problem statement is we've been working to produce a machine learning model that solves a medical issue that currently physicians don't have a reliable and quick way to identify vestibular issues. So with Oculogica's provided eye box exam data, we are trying to train a model to diagnose vestibular concussion. So I'll pass it off to my team for the rest of the demo.
Hi, I'm Ryan. I'm one of the backend developers on the team, and I'll go over our first data visualization, which is the correlation matrix. And we decided to use this matrix in order to identify possible similar features. And according to the correlation matrix, there seemed to be direct correlations between the left and right eye data, specifically position and velocity, which makes sense. Our bodies naturally move each eye the same way to focus on the same object. And there were also similar correlations between radial velocity, acceleration, and jerk, which also makes sense because acceleration is derived from velocity with respect to time, and jerk is derived from acceleration with respect to time. So it makes sense that these features have a high correlation. And because we want to avoid overfitting, we decided to omit a number of these features because they were too similar and could possibly contribute to the model training on repetitive data. Essentially, if the model trains on similar data twice, it will become more dependent on the training data, and that could lead to overfitting. And now I'll hand it off to Evan for the pie charts.
So in our data preprocessing, we were told by Joel at Oculogica to choose an arbitrary threshold to decide between a positive or negative diagnosis based on the number of abnormal measures observed for each patient. The following pie charts display the distributions of positive and negative diagnoses given thresholds of 3, 4, and 5 abnormal measures out of 9. As you can see, the percentage of negative values increased at higher threshold values. Since the most balanced distribution of positive and negative values is at a threshold of 3 abnormal measures with 46% negative diagnoses and 54% positive diagnoses, we chose it as our threshold for pre-processing the data. And I'll hand it off to the rest of my team for the scripts.
So at the beginning, we mount our Google Drive where we pull our scans and our master set from. That's our VVE clinical dev set. It has the num measures of norm, which is what we based our upper and lower threshold off of, and also as the file name. So we define our sample length, our upper and lower thresholds, the number of features we're taking out, which is 6 positions for each eye, and the radiuses of the pupil. Our data testing percent defines the amount of percentage, like the percent of the data that we're putting into the testing set. A step size of 2 means that we took it's pulled at 600 hertz, and then we stepped that down to 300 hertz. We were told we could take it down to a minimum of 167 hertz, and dropping down to half is where we got our best results. We defined the number of training sets we're going to have. I'll talk more on that later. We defined some more variables. VVE PD.read CSV, so that goes into our master set, pulls the file name and then modifies it to the scan file name, and because we got a big list of scan files and they didn't exactly match. So we take it, we edit it, so that way we can line it up with the scan file, and then we match those two. We take the information out of the scan file, scan contents equals pd.read_csv scan file, and then you can see we implement the step size. So we take a row, step 2, and then take a row. Feature frame equals scan content, so that's our 6 features. We dropped the empty values because one of the issues that we ran into is a lot of the scans would have missing values. Sometimes half of it would be empty on the extreme side. That's also why we couldn't have a super long sample size, because then you would just miss whole patients. So then for our file count and training sets, so we take the data, we figure out if it's positive or negative based on our threshold, and then we add it to the training set until the training set is full, as we defined up there as 153 this time. And then after the training set is full, it starts getting put into the test set. And then after this loop, we define the length of positive and negative samples, because that gets printed out after it's run. So you see how many of each you have that you're working with. Sample count, non-positive. That's more, it'll get printed out at the end. That's about it. Should be running it, I believe. I'll pass it off to the rest of my team.
So for the prediction strip, we also define a bunch of variables at the beginning in order to set certain parameters. The sample length is still 25,000 since that was what we trained on. We take a specific file and then we run that through the almost the same pre-processing. It adds them to a temporary list here, which is then transformed into a NumPy array later. And the NumPy array, you load the model, and the model forms a prediction based on every sample that you took out of the original file. And then we use a majority vote to determine a final diagnosis. So here you have a scan that has a VVE num measured abnormal of rating of 9. So if you run it as you run it through this, then it gives you an output of yes, they do have a concussion. So since it has 11 samples, then it runs it 11 times, and all of them came back as positive, so it outputs a yes. And if it is a negative, so this one has a num measures rating of 0. So if you run that, then it gives you a output of no. And that's all for the prediction script. And now Braden's going to handle the next step.
Thank you. So before the next steps, I'd like to reflect on the 10 weeks. Since our team has been exposed to a time series classification problem, we now understand the real-world application of time series classification and how it can be used to solve real-world problems. Prior to these 10 weeks, everyone on our team had little to no experience with time series classification. Now we know how to pre-process data to make it readable by a model and train this model to make accurate predictions based on the data it was given. We also learned how to use many types of models like CNNs, AutoKeras, LSTMs, and most importantly, MiniRocket. Now in terms of next steps, although we are done with demoing our model, we still plan on tweaking the sensitivity and specificity to reach higher and more balanced values and manipulating our scripts to get better performance metrics. Now, before we go, we'd like to thank AI Camp for providing us with this amazing opportunity to be able to work on this project and learn so much in these 10 weeks. Thank you.